Hi guys, welcome to the what. So today we will see MATLAB simulations on a single phase full bridge inverter, and we are triggering the semiconductor switches using sine pulse width modulation, right? So in the earlier video we saw how to trigger or how to turn on the semiconductor switches using a square wave, right? So this time we will see how to turn it on using a sine pulse width modulation. So let's get started. So we know that an inverter is a device or a power electronic converter which will convert DC to AC, right? We know the basics of the inverter. In this video we are focusing on sine pulse width modulation. So these are the things that we required. So all the things are same only. We will need a DC voltage source. We will need RLC series branch. We will need voltage current measurements, IGBTs, triangular wave generator, as well as sine wave generator. Right. So we will use these two: gain, constant, comparator or relational operator, scope, display, power GUI, ground, add block, and multiplexer. Right. So how this will work? So we have two different wave generators. So first one is the triangular wave generator. Second one is the sine wave generator or sinusoidal wave generator. Right. So the first one is our carrier wave, that is the triangular wave generator. So we are fixing this at a particular high frequency in kilohertz. So we are fixing this, for example, let's say we are fixing this as 10 kilohertz, and this sine wave generator is our modulating frequency. So this would be 50 hertz, that is the power frequency, right, that we need as the output. So the basic concept of this is a triangular wave. So we, in the earlier videos, what we did while generating a square pulse width modulation, we were comparing this triangular wave with a constant, right? So like for example, this is a 75%, this is a 25%, right? So we were changing the duty cycle using the constant as well as a triangular wave. But this time we will not do this. Instead, we will compare it with a sine wave. So we will compare a sine wave as well as a triangular wave. So let's say it will start from here, and the triangular wave is of high frequency and the sine wave is of power frequency. So it will move in such manner. So it will go something like this. This is, I'm only drawing the positive half and some of the negative half. I'm not completing the cycle, right? This is the 0. So if we compare these, what we will get? We will get some gate pulses here. Whenever this triangular wave is greater than the sine wave, then we will get a 0. And at this time, when triangle is smaller than the sine wave, we'll get some positive, something like this, then a 0, then something like this. Right. Now, this big one, here small, here big. Right. So we can see that the pulse width of the pulse width modulation is not constant. Right. So we saw in square pulse width modulation, the width is always constant, But here the width is not constant. It will move in the frequency of our power frequency, that is 50 hertz, right? So let's see the simulation, and there we will see at how this whole thing will work. Right? So let's take all the things that we need. So need one DC voltage. We'll need RLC branch, series branch. Let's take the measurements. Let's take current measurement. We'll take IGBT, that is the power IGBT that we will use. We'll use this one. Triangular wave generator. Sine wave generator. Not this one. This one actually. Gain. Constant. We'll use constant when required. Right? So we are not taking it right now. One relational operator or comparator. Display. Our GUI. Ground. It is important to select the correct ground when we use this. We will not use that block as of now. We will not use mux as of now, that is a multiplexer. Or let's just take it. So we got all our components. So let's start. The basic diagram of the inverter will remain same. Okay, you don't have to do anything on that. This triangular, IGBT, current measurement, voltage measurement, DC source. So just copy these IGBTs, put them in position. Use RL this time because we can only see the effect of sine pulse width modulation in the output current, and the output current will behave according to the load. So we are taking RL load, so it will replicate our real life situation, while most of the load that we use domestically are RL loads, right? So let's take 0.01 Henry, 10 ohm. That's enough. Let's connect this ammeter. Voltage across the load. Let's see. First of all, let's see the triggering circuit. As we know that the basic circuit of this inverter is same only. So the main focus right now is our triggering circuit. Right. So let's try to compare these. Sine. So for the triangular waves, frequency would be high frequency, that is 10 kilohertz. And here frequency is the power frequency, but we are asked the frequency in radian per second. So what we will do, we know that if we multiply our frequency in hertz with 2 into pi into our frequency, then we'll get in radians per second, right? So let's apply this and let's see what we are getting. We'll only run this for few cycles, few power frequency cycles. So we're directly getting these in the gate pulse only. But let's see the output. Now it will show us. Oh. So if we see the first graph, I'll just zoom it in for the first cycle. What we will see a high frequency triangular wave in the background, and the modulating wave is the sine wave, right? So whenever, like if we see the second graph is the output gate pulses, right? So if I zoom it in, so then we can see here the width of the gate pulses will depend on the amplitude of the sine wave. So if the sine wave is at full amplitude, that is 1, the width is almost full, right? Means almost 100%. And if we see some negative cycle, here we can see that when the sine wave is at -1, the width is almost 0, right? But if we zoom it in, we can see that we are not getting any width here. This is so small, right? It is 0.014875. So this is so small. So to overcome this, we need to do one thing. We just need to multiply this sine wave with such constant that it will not reach exactly -1, or it will not reach exactly +1, right? So the modulating wave should be little bit less in amplitude than the carrier wave. Otherwise, we will not get the perfect outputs, right? So as I explained you here as well, if we see, then we can see the width is so small, right? So for that reason, so let's put this multiplication in this sine wave and multiply this with 0.99, right? So it will be smaller than 1, right? It will not reach 1. Now let's see our output. We will not see exact output. Here we can see that some amount is, see, here we can see the blue line is not crossing the tip of this triangular wave, right? So we actually want this. So now we can get our beautiful output. And as we see the gate pulses, we can see that the width is not equal. It will be according to the amplitude of the sine wave, right? So now let's connect the IGBTs. Let's take one logic operator for NOT gate. NOT gate will be here. NOT gate will be here. Not here. Good. So let's apply the gate pulses. This and this. NOT gate should connect with this, and right. And let's check. Let's take our output. As we know, we'll see four outputs, four different figures. The first one would be the main gate pulse, second one would be the NOT gate pulse, third one would be the voltage across the load, and fourth one would be the current across the load. Right? Let's measure the voltage. We are applying 100 volts DC. Right? So now let's run this for 3 cycles. So we are getting 98 value, or I just forgot to quote RMS, but it doesn't matter. We'll get same only. Now if we open the main thing, this was the thing that I was talking, that the output, as we see, is in a sine wave in voltage as well as in current, right? So we were not getting such output while we were doing with square pulse width modulations. So here we can see, if I zoom it in, let's run it for a few more cycles. Now we can clearly see that it is a sine wave, but it is not exactly sine wave. It is just a representation of sine wave. If we zoom it somewhere here, we can see the output will depend on the gate pulses. If I zoom in one whole cycle, we can see that the output will depend on the gate pulses. And we know that the inductive load, RL load is there, so current and voltage will not be in same phase. There will be some phase difference, right? So we can see here, whenever the voltage is increasing, the current is decreasing, so it is out of phase. So that is also correct. Our gate pulses are opposite to each other. Yeah. So, okay. So they are not opposite. Yeah, this would be opposite. So now we can say that the gate pulses are opposite. We see that. See, wherever the upper one is positive, the lower one is negative, and according to it, the voltage and current will differ. Right. So this is the representation of MATLAB simulations on full bridge single phase inverter using sine pulse width modulation. So if you have any doubts, just do let me know in the comment section. Right? I'll try to address you all. So for now, take care. Bye bye. Thank you.